Hello, and welcome to our IWOCL and SYCLcon 2021 talk toward a better defined SYCL memory consistency model. My name is Ben Ashbaugh. I'm a software architect at Intel. Though I am giving this presentation, this work was a collaboration, and I'd like to thank and acknowledge my amazing coworkers, James, Mike, Greg, John, and Roland, who helped to develop this content. This talk is roughly divided into 5 sections. We'll start by looking at what is a memory model and why is a memory model important. We'll look at what was in SYCL 1.2.1 and what might be some of the areas for improvement. We'll look at some other memory models for inspiration, like the C++, Opencl, and Vulcan memory models. We'll look at what we added in SYCL 2020 to improve the SYCL memory model. And finally, we'll close with a discussion of interesting topics and questions to discuss for the next version of SYCL. So what is a memory model and why does a memory model matter? Well, it turns out your code may not execute exactly as you wrote it. Some examples. A compiler is going to compile your program, and as part of that compilation process, the compiler may reorder your instructions to something more optimal. When the hardware executes your program, the hardware may further execute instructions out of order. As your program is executing, there may be caching effects. Some devices have multiple levels of caches, and in a heterogeneous programming model like SYCL, some devices have their own device-specific caches. Now, as long as your program is executing in a single thread, this isn't observable, and your program executes as if it were executing the exact statements that you wrote. But once multiple threads are executing your program, some of this becomes observable. A memory model is a contract between an application developer and an implementation to constrain this uncertainty. It guarantees behavior for application developers so that they can write their programs with confidence, and it describes valid and invalid optimizations for implementers so that they can get the best performance out of their devices. Here is an example to motivate why a memory model is important. Let's say that we have two variables, x and y, and we've initialized both of these variables to 0. In thread number 1, which is our producer thread, we're first going to store the value of 1 to x, and then we're going to store the value of 2 to y. In thread number 2, which is our consumer thread, we want to know if we observe the store to y, so if we see that y is equal to 2, can we assert that the store to x has occurred as well? So can we assert that x is equal to 1? As you may have guessed, the answer is no, and that's unfortunate because that could break some algorithms. Some reasons why were listed on the previous slide. Maybe in thread number 1, the compiler decided to schedule the store to y first. Or maybe in thread number 2, the value of x was in the cache, so when we read the value of x, we get back a stale value. A memory model is going to describe how to make this okay, so that our program can safely assert that x is equal to 1 when it's needed, or so that an implementation doesn't have to ensure that x is equal to 1 when it's not needed. Ultimately, a memory model ensures that we see the values in memory in an order that we expect to see them in. So we actually joked that perhaps an alternate title of this presentation should be Better Memory Model, a SYCL we need. But we decided to go with a more formal title instead. So what was in SYCL 1.2.1? Well, SYCL 1.2.1 was intended to layer upon Opencl 1.2, so the SYCL 1.2.1 memory model was closely derived from Opencl 1.2. And what the Opencl 1.2 memory model guaranteed is that we can have memory consistency within a work group by using a fence or a barrier. So this is an example that looks a lot like the simple example on the previous slide, where in one work item, which is kind of the equivalent to one thread, we're first going to store the value of 1 to x, and then we're going to have our memory fence, and then we're going to do a special atomic store when we write to y. So we're going to use the atomic store to store the value of 2 to y. In work item number 2, which is kind of the same as thread number 2, we're going to do a special atomic load, and if that atomic load sees the value of 2, we can have a same memory fence, and then we can guarantee that our assertion is okay. Well, probably. We actually have no guarantees. The Opencl 1.2 memory model, and hence the SYCL 1.2 memory model, was not very well specified, so we think this is correct. This is our interpretation, but it's possible that there are other interpretations too, and on some devices this may not actually be okay. We also know that in SYCL 1.2.1, we can't guarantee memory consistency across workgroups or kernels. So if work item number 2 happens to be in a different workgroup, then our assertion no longer holds. And that's a little bit disappointing. So we'll look at how we can improve this in SYCL 2020. In order to get there, let's look at some other memory models that we can use to inform what we do for the SYCL 2020 memory model. We'll start by looking at what's in C++11. C++11 is the first version of C++ that formally defines the behavior for multiple threads of execution. And this is really great because many of the same concepts that apply to C++ programs executed by multiple threads are directly applicable to SYCL data parallel programs. For example, C++11 formally defines key concepts like memory locations, conflicting actions upon those memory locations, and data races. C++11 formally defines relations like sequenced before, synchronizes with, and happens before, and describes how to reason about programs using these relations. C++11 formally defines the concept of a memory order that constrains memory accesses around atomic operations, and defines the sequentially consistent, acquire and release, and relaxed consistency memory orders. The subsequent slides will show how to use the C++11 atomic classes and the atomic thread fence function to implement the C++11 memory model. Let's look at an example that uses the C++11 atomic classes. This example is intentionally very similar to the naive example we went through before. In this example, we have an ordinary variable x, which we've initialized to 0, and we have a special atomic variable y, which we have also initialized to 0. In thread number 1, which is our producer thread, we store the value of 1 to x, just like we did before. When we store the value of 2 to y, though, we're going to do it using a special atomic store function. And this atomic store function is sequentially consistent by default in C++. In thread number 2, which is our consumer thread, we're also going to use a special atomic load function to load the value out of y. Now, if we load the value from y and we see that the store has occurred, so we see that the value of y is equal to 2, now we can safely assert that the value of x is equal to 1, so that the store from x has also occurred. So let's figure out how that happens. The first thing is that the store to y and the load from y are going to synchronize with each other. They have a synchronize with relation. Furthermore, we have two sequenced before relations. The store to x is sequenced before the store to y, and the load from y is sequenced before the load from x. Now, if we take both of these together, we can say that there is a happens before relation that's going to guarantee that the store to x happened before the load from x, so we can safely assert that the value of x is equal to 1. So what does sequential consistency mean? Well, informally, it means that there is one modification order and all threads agree what it is. So let's look at an example. In this example, we'll have two atomic variables, x and y, and we'll initialize them to 0 like usual. We'll have two writer threads. The first writer thread is going to store the value of 1 to x, and the second writer thread is going to store the value of 2 to y. Now these threads could execute in either order, which means that the store to x may occur first, or the store to y may occur first, and we don't know which one's going to occur, but we do know that because these are sequentially consistent stores, all threads are going to agree what the order is. Let's say that we have one reader thread, and this reader thread is going to read from x first, and then it's going to read from y. And furthermore, let's say that this thread read the value of 1 from x, and it read the value of 0 from y. So we know that in this particular execution, the store to x occurred first because the store to y hasn't occurred yet. Let's also say that reader thread number 2 is going to load from y first, and then it's going to load from x. And furthermore, let's say that this reader thread has observed that the value of y is equal to 1. The question is, what, if anything, can we say about the value loaded from x? Well, in this case, because this is sequentially consistent stores, we can guarantee that the value of x must also be 1 in this case, because we know that the store to x has occurred before the store to y. Or said another way, we can say that the write to y happened after the write to x. This is very intuitive, which makes it a very attractive memory order, but it's also very expensive to implement on some architectures because all threads have to agree what was the total modification order. So because the sequentially consistent order is expensive on some architectures, C++ provides some alternatives. And one of those alternatives is the acquire-release memory order. So this is a simple example similar to the one before, where we have an ordinary variable x and an atomic variable y, and we've initialized them both to 0. In this case, in thread number 1, we've stored the value of 1 to x like usual, and we've also stored the value of 2 to y, but in this case we've used a special non-default memory order called the release memory order. In thread number 2, which is the consuming thread, we also use a special atomic load, but in this case we use a special acquire load instead of the default memory consistent load. And what's pretty cool about this is that this provides the same guarantees as the sequentially consistent order in this case, and we can safely assert that x is equal to 1. Said another way, we have the same synchronizes with relation between the load and the store. We have the same sequenced before relations between the stores and the loads. So we can have the same happens before relation between the store to x and the load from x. So if the previous example that used acquire and release memory orders behaved the same as the example that used sequential consistent atomics, what's the difference between the two? Well, informally, the acquire and release memory orders order the memory stores within threads, but not necessarily across threads. So let's go back to our previous sequential consistent example. We have the same two atomic variables, x and y, which we have initialized to 0, and we have the same two writer threads, which are going to store the value of 1 to x and y, except in this case, they're going to do the store using the release memory order. We have the same two reader threads, reader thread 1 and reader thread 2, and in reader thread number 1, we're going to read x first and then y, and reader thread number 1 is going to see that the value that's stored to x occurred before the value that was stored to y. So it sees that x is equal to 1 and that y is equal to 0. In reader thread number 2, we're going to read from y first and then from x. And reader thread number 2 just so happens to see that the value of y was equal to 1. The question is, can reader thread number 2 make any inferences about the value for x? And it turns out in this case it can't, because reader thread number 1 and reader thread number 2 can disagree about the modification order. Just because reader thread number 2 saw that the value was stored to y first doesn't necessarily mean that it also saw that the value from x has also occurred. So what about relaxed consistency? Well, relaxed consistency atomics do provide read, modify, write atomicity for things like atomic increments or compare and exchanges or other operations. But relaxed consistency atomics provide no happens before relation, and hence there are no memory consistency guarantees. These are still useful. I don't want to say that they're not, but only in some limited cases for things like reductions, histograms, bump allocators, counters, progress bars, etc. As one example, let's say that we have an atomic counter, which we've initialized to 0, and then we're going to perform 100 atomic increments on this counter, possibly from one thread, possibly from multiple threads. We can definitely assert that after those 100 atomic increments occur, that the counter is equal to 100, because we have the read, modify, write atomicity. We just can't make any inferences about memory operations around those relaxed consistency atomic operations. So this seems really great, and it's tempting to say, we'll just use the C++ memory model as the SYCL memory model. Well, it turns out that the C++ memory model has some limitations. The biggest is that the C++ memory model assumes that all memory is visible to all threads, and that's not necessarily true for SYCL devices that may have device-specific memories, or for SYCL address spaces, like the local address space is only visible to work items in a workgroup, and the private address space is only visible to within a work item. Still, the C++ memory model is a great basis for the SYCL memory model, so we'll borrow a lot of concepts from C++ 11. And that's good because we want to be compatible with C++ anyhow. So let's shift gears and look at another memory model, the Opencl 2.0 memory model. The Opencl 2.0 memory model is based heavily upon the C++11 memory model, or the C11 memory model, because Opencl is a C-based language. It reuses many of the same concepts like a memory location, or a conflicting action, or a data race, or the concepts of memory orders. It also reuses many of the relations like sequence before, synchronize with, and happens before. One of the key additions in the Opencl 2.0 memory model is the concept of a memory scope. The memory scope can constrain memory consistency to a subset of the threads or work items to improve performance. For example, it can constrain memory consistency to only the work items in a work group or the work items executing on the entire device instead of the work items executing on all devices. Another key addition is the concept of memory flags, which can further constrain memory consistency to improve performance. For example, memory consistency can be guaranteed for global memory or local memory, or both if needed. Here are some examples using the Opencl 2.0 memory model. This is an acquire and release operation that's going to work on all work items in the work group. You can see that it has the acquire and release memory order, and it has the memory scope work group. We can also have sequentially consistent operations, just like in C++. This is going to have a sequentially consistent operation for all work items. This one's going to be on all SVM devices. And finally, we can have a release fence that's going to work on global memory and local memory for all work items in the work group. And if we wanted this release fence to only work on global memory or to only work on local memory, we just need to change the memory fence flags. So this sounds really great too. It sounds like we took C++11, used that as a base, and added in some key features for execution on data parallel accelerators. Unfortunately, Opencl 2.0 had some problems as well. The first is that the Opencl 2.0 memory model was cumbersome to use. It added these atomic types for things like atomic ints and atomic floats, but because these were separate types, it didn't easily support mixed atomic and non-atomic accesses. More important, or more significantly, the Opencl 2.0 memory model has separate happens before relations for different address spaces. So what this means is that a flag in one address space, like the global address space, cannot enforce consistency in another address space. In compounding this problem, Opencl 2.0 also added a generic address space, so you didn't even necessarily know through code inspection which address space a flag was pointing to and which address space the memory operations around a flag were pointing to. These limitations are documented excellently in a paper from 2016 from Batty et al. That I would highly recommend reading. Here's an implication of a separate happens before. Note that in work item number 1, which is our producer kernel, we have a store to global memory. So this is storing the value of 1 to global memory. And the store of the atomic flag is in local memory. So we're storing the value of 2 to the flag in local memory. In the consumer thread in work item number 2, we have the proper load. So the load is done with the acquire memory order. And this all looks okay. It looks a lot like the example we had before. We have the synchronizes with relation. That's great. But unfortunately, we don't have the happens before relation because these are occurring in two different address spaces. So therefore, this actually isn't okay. We can't assert that work item number 2 will see the store to X. And that's really unfortunate. It isn't completely catastrophic. We can write code that is correct with the separate happens before relation, but it's really awkward to do so. In this case, we have the same store to X. We have a work item fence that's working on both address spaces, and we have a synchronizes relation between the producer work item and the consumer work item. We have atomic operations that are going to provide the necessary sequence before and happens before relations. So we can get the behavior. We can assert that work item number 2 will see the store to X, but it's very cumbersome to do so. One final memory model to consider is the Vulcan memory model. The Vulcan memory model is also based upon C++11 and C11 and also adds the concept of scope and memory regions in the form of storage classes. Some of the key additions in the Vulcan memory model are the concepts of availability and visibility. As you can see in the table below provided by the Vulcan working group, there is a mapping from most of the C++ memory orders to the Vulcan memory model semantics. Unfortunately, there is not a mapping between the sequentially consistent memory order and the Vulcan memory model semantics, and that's a bit unfortunate because sequential consistency is the default memory order in C++, and we want to stay compatible with C++. Therefore, the Vulcan memory model isn't suitable for a SYCL memory model as is. There has been a lot of great work by the Vulcan memory model TSG though, including formal modeling of the Vulcan memory model using the alloy relational model, so we still think there is a lot to learn from the Vulcan memory model. So now that we have an understanding of the concepts in memory models and some of the memory model inspirations, let's take a look at what is in SYCL 2020. Fundamentally, the SYCL 2020 memory model is a significant improvement over the SYCL 1.2.1 memory model. It is aligned well with C++20 and reuses many of the terms and the syntax from C++20, including atomic ref and atomic fence. It's also aligned well with Opencl 2.0. It includes the concepts of memory scopes and memory regions for performance. One of the key differences is that SYCL 2020 has adopted a single happens before relation for all memory regions, so it avoids some of the complexity in the Opencl 2.0 memory model. This slide gives a flavor for the SYCL atomic ref class, which should be familiar to C++20 programmers who are familiar with the C++20 atomic ref. Fundamentally, it's very similar to C++20, except it has several additions that are unique to SYCL. It includes an order and a scope, similar to Opencl, that can be used to improve performance. It also associates an address space with the reference object. The default order and the default scope are also specified per atomic ref, but they can be overridden per atomic operation. One of the limitations to be aware of is that the SYCL atomic ref class doesn't have support for synchronization. So there's no support for wait, notify one, notify all, etc. Because SYCL 2020 is targeting diverse architectures, SYCL 2020 also added device queries to express the capability of SYCL devices, and also context queries to express the capabilities of combinations of SYCL devices. One example would be some devices may not support the sequential consistency memory order, so these devices would not include sequentially consistent in its supported memory order device query. But even if there are two devices that individually support sequential consistency, maybe they cannot enforce sequential consistency across the devices. In that case, the devices would support sequential consistency in their device queries, but the context would not include sequential consistency in its context query. Everything in the presentation so far has been a look back and has looked at how we've solved problems. This section is a look toward the future and some problems we have not solved yet and how we may solve them in SYCL next. One interesting question to ask is, what differences remain between C++ and SYCL? The good news is that the default behavior of SYCL is now very close to C++17 and is aligned well with C++20. We do have some different consistency guarantees at different scopes depending on device capabilities, but the memory consistency guarantees generally follow C++. One of the remaining differences is the visibility of SYCL allocations, which is also tied to scopes. For example, private memory is currently only visible within its work item, whereas C++ defaults to system visibility. Should SYCL next change its defaults to align better with C++, say by allowing private memory to be accessed across work items or local memory to be accessed across work groups? Another interesting area to investigate involves the intersection between the memory model and the execution model, and specifically the concepts of forward progress. This kernel is one that many SYCL programmers have probably tried to write. In it, a leader among a group of work items is elected to go off and do some work, and while the leader is doing its work, the other work items are going to sit in a loop. Unfortunately, even though this code is correct according to the memory model, and is syntactically correct and will compile, it probably won't execute correctly on mini SYCL devices because mini SYCL devices lack the necessary forward progress guarantees. So perhaps we should consider some new language features to help developers. Maybe we could have some queries for forward progress guarantees so a device could advertise what it supports. And perhaps we should support some kernel attributes so a kernel can describe which forward progress guarantees it requires. So in summary, and my call to action, SYCL 2020 has a significantly improved memory model. It is syntactically aligned with modern C++ while incorporating concepts of scopes and address spaces from other memory models to improve performance. SYCL 2020 adds queries for devices and context to support a diverse set of device capabilities and combinations of those devices. All of that said, there's still work to be done and we are looking for your help. The SYCL 2020 memory model would benefit from formal modeling to prove correctness, similar to other memory models. Looking out into the future, we should investigate forward progress guarantees to ensure correctness and to further improve portability of code written in SYCL. I'm sure that's not all though, so if there are other features that you need for your code bases, please let us know. And finally, just to call out to the academic community specifically, many parts of SYCL could benefit from research projects, so please don't hesitate to reach out. Thank you very much for your time, and I hope you enjoy the rest of IWOCL.